All right, I'm back. So we're going to go back into Ableton here with a very similar project, and we're going to start doing some frequency modulation synthesis. And then we're going to maybe explore some of the presets, or we might do that in class. Now, this is building off of the videos I've posted and the study guide. So please have looked at that, otherwise this might be pretty confusing for you. What we're going to start to do is use these oscillators and look at some of these algorithms and why they're useful. Okay, so let's just pretend, let's go back to vibrato. So I'm going to turn on A, destination A. I'm going to turn off destination B. I'm going to go 100%. So what frequency modulation is a very big, very fast vibrato. And it is so big and so fast that it ends up not sounding like one pitch that's going up and down. It ends up sounding like multiple pitches at once, and it creates sidebands. If you looked at that equation, sidebands occur at integer multiples of the modulator, at C plus the carrier frequency plus modulator times 1 times 2 times 3 for the sidebands. And let me put a spectrum on so we can look at this while we do it. Okay, so let's just look at what we have so far. I'm going to turn off the LFO. Oh, I better go to a sine wave. Look at that beautiful saw. We'll make our own saw. How about that? Okay. So we get that impulse, and it shows a pretty even distribution. But overall, we have one dominant frequency, and it's at 100 hertz. Pretty much exactly. That worked out well. Okay, so then if we start to go in too much. And you can watch it shift back and forth. There we go. I had to make it go a little faster. Now, this is tough to use because we don't know what the ratio is. We don't even know what the amplitude is exactly of the LFO. So what's cool about Operator, which is based on the DX7, is it can use just a normal old sine wave oscillator to modulate another one. And we can do our ratio right here. So if this is at 1 and then 2, it's now a carrier to modulator ratio of 1 to 2. And with this current algorithm, you look at these colors. These colors are important. Green is going to modulate yellow. Green to yellow right here. Green to yellow plus then orange to yellow. It gets pretty complicated. It's hard to predict what they're going to sound like. But in the standard algorithm that it starts with, D is going to modulate C, and then the modulated C is going to modulate B. Modulated B is going to modulate A. But let's make it simple. We're going to have two oscillators, okay? And the ratio right now is 1 to 2. The level of the modulator, which is B, is going to affect how many sidebands we have. So if it's really high, we'll have a lot of sidebands. If it's not high, we won't have too many. So now we have this really clear ratio. And if we wanted to make it 1 to 2.30 out of, what does it go out of? Out of 1,000. Okay, so that's like a 3% increase. That's going to give us some inharmonic tones, but let's make it harmonic first, okay? So, and we'll even make it 1 to 1. So that, according to the study guide, should give us something similar to a sawtooth wave. It should give us each integer multiple of the fundamental. And the fundamental was at 100, so we should see something at 200, 300, 400, 500, all that. Let's try it. Okay, got another spike right here. Here's 200. And then kind of a spike right here, about 300. But let's make it a little bigger. Yeah, now it's starting to look like it. I want to make one long note. too big, otherwise it'll take over. Here we go. Isn't that a beautiful saw-looking wave? So these are all the sidebands. We have the fundamental at 100, and then we have 100 plus, oh, it's a 1-to-1 ratio, so plus another 100. That'd be C plus M equals 200. Then we have C plus 2M, which would be 300. And then we have C plus 3M, which would be 400. And we get this nice, each of the harmonics is outlined just like a sawtooth wave. And we could compare that to a normal sawtooth wave by doing this. And doesn't that look familiar? So we don't even need these different wave shapes. We could do it just with sine waves. All right, let's bring this one back in. Okay, so if that is how we do a sawtooth wave, remember, if we do a ratio of 1 to 2, we will get just the odd order harmonics, which some find preferable. So that would be like a square or a triangle wave. Depending on how high the level is, will determine if it sounds more like a square or a triangle. So let's try a low level. That should correspond with the triangle wave. And we're skipping 100, 300, 500, 700, 900, blah, blah, blah. And then it falls off. Now if I crank this up, a little more like a square. We don't need all that. Now this has to do with the lower sidebands. There is a Bessel function we could use to calculate the amplitude of each sideband, and then remember there are negative sidebands as well that then count as out of phase upper sidebands, and it gets confusing. So don't worry about that. I won't quiz you on that. You don't need to know it, but if I just want to explain why it goes up and down just a little bit. Okay, so we just made a triangle, square, and sawtooth wave with just frequency modulation. Now, if we wanted to make something like the real world does not exist in such perfect ratios, so let's try adding a little bit of fine-tuning to make it not so in tune, actually. It's going to actually detune our instrument a little bit. Ooh, we're getting gross here. Now we're back to kind of a sawtooth wave, but with a steeper dip in between each one. So this would all be all the way up at an additional 1. So that would be putting fine at 1,000. It would be like making this 3 instead of 2. Let's try just a little bit. See, sometimes a little bit is more painful than a lot. And we could work our way through. And we could start getting really gross if we add this one in. Now let's make this a really high one. Changing our upper frequency contact. Look at that hump there. Interesting. Not very audible though. Is it being filtered out? Is that why? Yeah. So what normally would happen with something like that would be a really short attack. So it's just when it comes on, or a really short decay, I should say, and a short attack. Oh, I'm so sorry for making you listen to the metronome. Yeah, that was good. How about, let's do a nice and low one. Well, see, the tough part about this algorithm is it's going straight down. Let's actually change up our algorithm a little bit. I want this, well, we could do one with no modulation. It would just be, we won't do that. Oh yeah, here we go. I like this one. So look, each of them is going to modulate oscillator A on their own. So it's going to be B times A, and they're going to have their own ratio with their own sidebands. C times A with their own ratio, their own sidebands, and harmonic content. And D times A. That's going to be a crunchy one. And this is where it gets really important to have envelopes for each of these. I'm not hearing this. Oh, that's why it's so quiet. Now they'll sound fatter and thicker if you detune them a little bit. And I want to show you real quick too, if you like working this way, you can actually make these fixed. And so 100 hertz, and then we'll make this one 200 hertz. We'll call it 199 just so it's not too perfect. And we'll make this one 300 hertz, close to it. And we'll make this one 50 hertz, which also does frequency modulation. And it is an integer still, but it's going to create just different harmonic content. And then the multiplier adjusted to the range. I didn't look at this before. This is used to adjust the range of the fixed frequency. Multiply this value with the... Oh, okay, so we could put it in a different octave. Ho! Jumping around really big. So we get that pop. We should make this one 10. Get that snap, and then it goes away, and then this comes in nice and slow. So if you like working that way, you can. It's not my style. And look, it saved what we had. That's nice. Okay, so let's explore some of these different algorithms here too. These are each going to multiply against oscillator B. I just don't know which one happens first. I think it goes left from right though. So it's going to have a result of C times B, and then the result of C times B is multiplied by D, and then that multiplies A. Do I know what these are going to sound like? No. You have to just experiment, and that's part of the joy of the DX7 and the operator, which is an exact clone of it. You don't really know what it's going to do. Once you get about 4 layers deep, it's more unpredictable. But you can guess. You can have a pretty good guess of how gritty it's going to sound looking at the fine-tuning here. I want to make one that goes out all separate with no modulation. That would be more like additive synthesis, where each of them is being added together in the end rather than multiplying against each other. And I'll go to this algorithm. So that serves kind of a different purpose. It's less about inharmonic and less about unpredictability. This is more straight predictability. All right, and thus far, we've done everything with just sine waves. But if you imagine, not only are the sine, if we did a different wave shape, not only would this fundamental frequency be multiplying against other fundamental frequencies, then we're going to get spectrum multiplying by spectrum. So let's make a sound with sine waves and then change them to sawtooth waves and see what happens. Make it nice and clean. Seems a little high in pitch. So now I'm going to switch let's just start with D, which remember in the algorithm is the very last one. Oh, does this change? Oh, it does change. That's cool when you change them in here so you can see what your algorithm looks like. Okay, anyway, sorry, I got distracted. We didn't even change it yet. That difference. Let's hear it in sine again. And then with the sawtooth wave, it takes a little bit for it to kick in. Okay, let's try this one with a square wave now. So remember, now it's not just each oscillator multiplying against the fundamental of each other oscillator. It is their spectrums multiplying. And if you can't predict what it's going to sound like, I don't blame you. It's almost impossible. You'll start to get the hang of it. It's really about envelope shape and whether or not you want it to be harmonic. And you'll start to really get a good idea just through experimentation. Now, what we could do is just look through and see how, because there are presets for operator, how they accomplish the things they accomplish. What is components? Huh, weird. All right, so let's look. What do they do for a mallet? Let's look at a long marimba. So that means it's sustained. What do they do here? Okay, so click on through. Oh, they're all sine waves. Let's look at their envelopes. Pay attention to the envelope. So this is the envelope of the main oscillator. That's the main sound. Okay, so it hits really hard, sustains lower, has a long release. All right, then it's multiplied by an integer, an even integer, so we're not going to get too many inharmonic sidebands. It's going to be mostly harmonic, and it would be like a sawtooth. And that one is right away. So it's a harmonic attack, and then it drops out. So the modulation goes down as the envelope goes down too. And then we have a similar, it's almost the exact same settings as B, but this one is slightly detuned and it sustains. And then way up high, 11 times the frequency of oscillator A, slightly detuned. Let's hear it. Okay. Let's go through and take them out one at a time. Oh, that click is way quieter. All right, let's try it without C. And I notice, look, they have a different algorithm too. So they are multiplying D times C. C would essentially just be an octave above A. And then A and B aren't being modulated by anything. Now tell me, look at this. If I turned off C, D is not going to do anything, because it has to go through C to even come out. So keep that in mind. All right, so it's a lot of the envelope, and this is what makes it have that ping, that plunk sound of a percussion, is having just a decay with no sustain. If we went like this, that still sounds pretty close. Let's do this one. I think it would actually sound more like a, we would just need more notes, because marimbas don't really sustain. But anyways, let's go to a bell. Bells have a lot of inharmonic spectra. Oh, it looks like they put a bunch of things on it. These are something we'll show you how to make a macro control field. It's just like an audio effect rack. They made it just to make it easier to use, I'm guessing. And there's an EQ. I don't want to talk about that one. Too complicated. There we go. Ooh, that's cool. So look, they have a fixed frequency here. What happens if I turn it up? Multiplier 0.0001. So this has to be really low. With algorithm, oh, it's coming out on its own. Turn it off, see what happens. Look at this envelope, too. Oh, what a peculiar one. So go through and... Oh, and they have all noise. 2 noises, 2 user-defined waves. You know, it's someone's job just to make these presets. So you can go through and look at these, try them out, see what you think. And sometimes it's best for part of the assignment, which is going to be recreating a synth sound. It's a lot easier to just find a preset and then customize from there. But the consequence is presets can look, I mean, I don't know how they made an envelope like that. Oh, I see. So that is just the attack. It starts at 0 dB. That's weird to grasp. But it works for them. And then decay. Interesting. Yeah, so go through and see how they use the presets. I mean, gosh, that's just the mallets. Let's look at strings. Oh, there's not very many. That's not what I want. They put a delay on it and stuff. Look at all these effects. Cheaters. No, it's not cheating. You can do it. So go through, experiment with some of these, and start to think about how you can accomplish in mimicking a sound with FM synthesis. You can make almost any sound with FM synthesis. Now, I'll tell you, once you get about 4 oscillators deep and they're all multiplying each other, it is tough to figure out what they are going to sound like. But just experiment and focus on the envelopes. That's the key. And remember, if you want it to be more in tune, these will all be at even numbers. Okay, oh yeah, we have harmonic spectrum, but it's all integer multiples, so it sounds, we can tell that, that is the root. But if I start going, what's the root? I can't tell. So you could really do the math and make like smiley faces with it. I've seen people do. Very confusing. So don't be intimidated. It's okay if you don't completely understand what is going to cause what result, but just understand the simple method of calculating sidebands for 2 oscillators. That would be the kind of thing that I would test you on, and that would be important to know how to do. But beyond that, just experiment with it and think about the envelopes. And just because you're frequency modulating, you can still use an LFO. You can still use a filter. You can still use a pitch envelope, whatever you need to do. But try it out a little bit. All right. Well, thanks for watching.